Hello everybody, we're going to look today at section 4.4, graphing trigonometric functions. We're going to use what we already know about the sine, cosine, and tangent based on our special triangles and the unit circle to try to come up with a picture of what that graph is going to look like. So the first thing that we're going to do is we're going to have you look at a few of the values and try to fill in as much of this table as you can without using your calculator. So you're going to use maybe the unit circle for the 0, the 90, 180, 270, and 360 to fill out the sine, cosine, and tangent. You can use the special triangles for the 30, 60, 90, 45, 45, 90, and then use the reference angles for your 120, 135, and so on. So take just a minute, pause this video, and go ahead and fill in as many as you can. Remember, we want you to know very quickly without using a calculator what's the sine of 30, what's the cosine of 45. And maybe you don't know them quickly for something like 315, but we want you to be able to figure it out. So you want to be able to look at that and say, oh, I know, I'm just going to draw the reference angle and evaluate it from there. So take just a minute, pause this video, and then come back to the answers. All right, here's the answers for our table if you're filling in based on both the unit circle and the special triangles. One thing that you want to notice as you fill everything in is paying attention to the quadrants where we know things are positive and negative. If we take a look at quadrant 1, we know that everything in quadrant number 1 is supposed to be positive. So here's our 90 degrees, and sure enough, if we check out everything in this first quadrant, there's not a single negative number in there. Now, when we were thinking about the quadrants where they were positive and negative, we had all, and then we had the STC going on here. And so that meant for us, now when we're in quadrant number 2, from 90 to 180, that the sine should be the only trig function that's positive. Sure enough, it is right here. Our cosine and our tangent are going to be negative. We can do that same thing when we look at quadrant number 3 as we're evaluating. In quadrant number 3, we're expecting the tangent to be positive. In quadrant number 4, we're expecting the cosine to be positive. And sure enough, all of the correct functions are the sign that we were expecting. Now that we have those values, what we can do is we can plot those values as if they are an XY coordinate pair. So the next thing that we're going to take a look at is what would the graph of the sine even look like? So if we were going to be plotting some of these points, we could say, hey, at 0 degrees or 0 radians, you see that we have degrees here in the table, but I have my graph listed in radians for units here. At 0 degrees, that y value is 0. So we're going to plot that as the coordinate 0, 0. And then at 30, we're up to 1/2 here. So 30 degrees, we're going to plot a 1/2. All right, at 45, we're at square root of 2 over 2. The square root of 2 over 2, by the way, if you calculate that, 0.707. So if we're at 45 degrees, we're going to be at about 0.7 here. And let's see, what's next? 60 degrees is square root of 3 over 2. On your calculator, you can figure out square root of 3 over 2, 0.866. So we can plot that at our 60 degrees. And then at pi over 2, or 90 degrees, now we're up at 1. As we keep going, 120, 135, 150, and 180 is all just symmetric, going back down. Square root of 3 over 2. Square root of 2 over 2, 1/2, there we go, and back to 0 here. So that's the first part of my sine graph, going up to 1 and then back down. Similar values, but now negative, right? This is going down to the negative part of the graph, negative 1/2, negative square root of 2 over 2. So we'll just plot those as we go, negative 1/2. Negative square root of 2 over 2, and then down to negative 1 at that 270 degrees, and then working our way back up again. And so we see then our picture of the sine, but thinking of them as coordinates that we're plotting them, just XY coordinate pairs. Now, if we use coterminal angles, remembering that 330 degrees would be the same as negative 30 degrees. Let's say that I would draw that in here. If I rotate it around 330 degrees in the positive direction, that would be the same as negative 30 degrees. So that telling me that negative 30 degrees would also have a negative 1/2. And that's why your graph going in the other direction is going to have the same sort of shape as you calculate all of the negative angles as well. So we're not going to plot all of those specifically, but you get the idea for how that's going to keep repeating itself because of those coterminal angles. So this turns out to be our graph for the sine function. Now we could go through this process for each of the other graphs for the cosine and the tangent as well. Okay. Now before we do that, let's take a look at what happens for the sine graph if we want to just evaluate or analyze, I should say, a few aspects of that graph. The amplitude. The amplitude is the distance from the max of our graph to the minimum of our graph. And so when we're looking at the sine function, it goes up to 1 and then it goes down to negative 1. And so the amplitude is the distance from what we would call the midline to the maximum or minimum point. And so the middle of this graph, the midline, is happening on the x-axis, so it goes up 1 and down 1. Another way to talk about the amplitude is to say that it's the maximum value minus the minimum value divided by 2. And so if we use that in this picture, the maximum value is 1, the minimum value is negative 1 divided by 2. Sure enough, 1 minus negative 1, or 1 plus 1, 2 over 2, gives me 1 as that amplitude. What is the period? The period is the length of time that it takes to complete one cycle. And so when we graphed that sine function, if we start at 0, 0, it goes through one cycle. It takes 2 pi radians, or 360 degrees, to do that. Note that we're not saying when does it get back to 0. It does get back to 0 at 180 degrees, but it hasn't completed that cycle. It's not repeating itself yet. So 2 pi, or 360 for your period. Domain, all the x values that I can put in there, that's negative infinity to positive infinity. There's not a single value where that would be undefined. This graph does not stop at 2 pi. It's going to keep on going, and I can always evaluate using coterminal angles, the sine of any angle that I choose. The range is the y values, and our y values go from negative 1 to positive 1, including both of those values. All right, the cosine, if we would go through and plot the points just as we did with the sine, our picture would end up looking like this. The cosine, you notice, starts at its maximum value of 1. The sine went through 0, 0. The cosine starts at its maximum value of 1. Has a similar sort of shape in terms of the values that you're ending up with, in terms of the positive 1 and 1/2 and square root of 3 over 2 and such. And so when we look at this graph, its amplitude is still 1. It goes up 1 and down 1 from that midline. It still takes 360 degrees, or 2 pi radians, to get through one cycle. Domain, same as the sine, negative infinity to positive infinity. Range, also same as the sine, negative 1 to positive 1. So it's not the same graph, but it has a lot of similarities. Mostly make sure that you note that this starts at 1 and the sine graph starts at 0 instead. The other thing that's nice to look at in these graphs is relating this to the quadrants where things were positive and negative. The cosine graph, we know if we're looking at that when we were drawing the quadrants where things were positive and negative, we had the STC happening here. And so we knew that the cosine is positive in the first quadrant. It's also positive again by the time we come back to that fourth quadrant. So check out this graph. Sure enough, the cosine is positive in quadrant 1 from 0 to 90, negative from 90 to 180, 180 to 270, and then positive again in that fourth quadrant. So the quadrants where things are positive and negative are evident in these graphs as well. If we look at the tangent graph is a little bit different than the rest of them, so you want to make special note about that. The tangent does not have an amplitude. Remember, the amplitude was the maximum minus the minimum divided by 2. But when we check out this tangent graph, this does go up forever. The tangent doesn't have a maximum or a minimum, and therefore there's no amplitude. So if you ever see the question, what's the amplitude of the tangent? That's a trick question. The amplitude is none because I can't find that value. The period of the tangent is a little different than the sine and the cosine as well. It only takes 180 degrees to go through one cycle. So each of these branches of the tangent, I'm going to call it, each of those branches are one period of that graph. In our domain of the tangent, it's almost everything, but you're noticing some undefined values in here, right? We could say that these are our asymptotes in here. We've got another vertical asymptote here. Sorry, that didn't get straight down the line. Here's another vertical asymptote here. Noticing that those are negative pi over 2, positive pi over 2, 3 pi over 2. The next one's going to be 5 pi over 2. It's basically odd multiples of pi over 2. So my domain is any number, all numbers, but x can't be equal to pi over 2 times k, where k is odd. Those odd multiples of pi over 2 are not going to be defined for your tangent function. Now, usually people are pretty familiar with the sine and the cosine function. The tangent is usually a little newer for us. So one way that I like to help remind people to memorize this is that when you look at just one cycle of this tangent graph, it kind of reminds me of the x cubed graph. And so if I draw a quick rough sketch of x cubed, I know that it looks like this. It crosses through 0, 0, and then it goes up forever in the positive x direction. As x goes negative, that's going down to negative infinity. So same sort of thing is happening here. We just have all of these different branches going along with it. But the middle part of this should remind you of the x cubed graph as one way to help memorize that. All right, now what we want to take a few minutes to explore is what happens as I make some changes to this equation. We looked at these same sort of changes when we were talking about the just regular polynomial functions back in chapter 1, whether something goes up, down, right, left, reflects, all that sort of thing. So that's what we're looking at here as well, but we're going to have a little bit different terminology that's going to go along with it. So we're going to start with the amplitude of the graph. In comparing that, what we're going to be looking at are a few of these different values that you have here. Sine of t, 2 sine of t, 3 sine of t. If we change to some of those values, let's take a quick look using Desmos. And in Desmos right now I have the sine graph in there. And what I'm going to graph instead, sorry you might not be able to see that first number, is what if I graph 2 times the sine of t? We'll use x here so that we get our graph here. When I have 2 times the sine of x, instead of the regular sine of x, let me put sine of x back in there for comparison. So the blue graph is our sine of x graph. The red graph is 2 times the sine of x. All of the zeros are in the same location. It's crossing the x-axis at the same location as it did before. But now the maximum value is up to 2 and down to negative 2. If I switch this red graph to be 3 times the sine of x, now my maximum value goes up to 3 and down to negative 3. Again, all the zeros in the same location. Now, when we multiplied a graph back in chapter 1 by a specific number, we called that a vertical stretch. And then the sine graph is a great example of how multiplying in front of that function vertically stretches your graph. You can see how this graph has gone up, stretched up to 3, stretched down to negative 3. Now what happens if I use a fraction there instead? What happens if I put 1/2 times the sine? Sure enough, now all of those y values are half as much as they used to be. So instead of this blue graph having a maximum at 1, now our red graph has a maximum at 1/2. Down here, same story. It's minimum was at negative 1. Now our red graph has that minimum at negative 1/2. And so multiplying by a fraction is now a vertical shrink instead. And if I put a negative number in there, let's say that I just start with doing negative x. Looks a little, from science, double helixy here, right? And so when you look at that though, our sine graph is the blue graph starting at 0, 0 and going up from there. Negative sine becomes just a reflection of that across the x-axis. And so the whole way along, it's a reflection across the whole thing. If I do negative 3, now not only is it stretched, to have a maximum of 3 and a minimum of -3, but it's also negative, meaning reflected across the axis. So instead of going up to start, this sine graph in red is going down to start. So that's kind of showing you what our amplitude is doing. The number in front of your sine function is helping to tell you what the amplitude of that graph is going to be. All right, now if that tells us about our amplitude, let's talk about the period. The length of each cycle is the period of your graph. In your notes, or in your homework rather, they're gonna talk sometimes about the frequency, and the frequency is 1 divided by the period, or the period is 1 divided by the frequency. Now I just showed you the sine function, and I'm gonna do that again for these graphs, but keep in mind the same properties are true for both the sine and the cosine when we're talking about these functions. Okay, so now when we look at the period, what we're going to do, instead of changing the number in front, we're going to leave the number in front to be 1 each time, but we're going to change the number that we're taking the sine of. So instead of just the sine of x or t or theta, whatever value we have, we're going to do 2t, 3t, and 1/2 t. All right, so let's clear this one out. We're going to keep the sine graph. I'll keep that in blue there. And now, as we said, we're going to do the sine now of 2 times x. Whoa, what happened there? Lots of squiggles happening here. So let's kind of analyze what's happening with our graph. The green graph is starting at 0, 0. Still going up to 1, still going down to -1, so it didn't change our amplitude. But now, how long does it take to go through one cycle? We go through one cycle by the time we get to pi. Before, when we were on the blue graph, it took us till 2 pi to go through one cycle. So this new cycle has a period that's half as long. So it only took us pi instead of 2 pi to get through one cycle. The other way to think about it is that it takes us, as we go through 2 cycles, we can go through 2 cycles in the same length of time that we normally would have only gone through 1 cycle. So when I'm sketching this graph, what I'm going to be able to show is to say 2 pi is the period, and now I'm going to draw 2 cycles of that graph, 2 cycles of it by the time I get to 2 pi. The same thing can happen if now I switch this to 3 pi. Or excuse me, 3x. If I'm going to put a 3x inside that parenthesis, again, it looks pretty squiggly, but think about what's supposed to happen. We didn't change the amplitude at all, and the 3x should tell me that I'm going to go through my cycles 3 times as fast, right? I'm going through my angle 3 times as fast as I was before. So if I look at how long it takes me to go through one cycle, following along here, oh, look at that. We were at 0 again by the time we're at 2 pi over 3, a third of the way to where we normally were, 120 degrees. So my new period is 120 degrees, or 2 pi over 3. And then if I keep on going, the other thing I want you to look at is that these green squiggles are going to go through 3 cycles by the time we get to 2 pi. Let's count them out. So here you can see where 2 pi is. And so now we've gone through, here's one cycle right here. Here's my second cycle right here. And here's my third cycle. So we go through 3 cycles in the same length of time that it took our original blue graph of the sine to go through one cycle. Okay. The last one for us to look at is, instead of having a 2 or a 3, what if we put a 1/2 in there? And if your guess was that it would be slower to go through one cycle, you would be correct. Right now it's going through the angles as half as fast as what it was before. And so when we look at this graph here now, the blue graph goes through one cycle by the time we get to 2 pi. That's our original sine function. That means the green graph is going to take twice as long. Follow that green graph along. It's going to take till 4 pi before that green graph gets back to its original starting point. And so now, instead of having 2 pi as its period, now we have 4 pi as its period. Okay. If we think about what that means for the period, well, we'll go back to that at the end again, but they say the sine of b times t. And so if we were going to think about what the period is, we know that the starting point of the period is 2 pi. And then whatever that number is that's multiplied by the t, and we're going to use b most often, we're going to divide 2 pi by b to come up with the length of that period. So in our original graph, the sign, this would be 1t, that makes your period 2 pi. When we had a 2 here, 2 pi over 2, that gave me a period of pi. When we put the 3 here, our period was 2 pi over 3, and so on. And so that's going to be our method to be able to figure out the period of each graph. All right, next one is the vertical shifts, and that's probably the most straightforward of our transformations. If we're adding or subtracting, that's just moving us up and down, right and left. For that sine graph, again, we could also use the cosine. It wouldn't matter which ones that we choose to do. So if we add 2 or 3, that's going to shift our graph up 2 and 3 units. If we subtract 4, that's going to shift us down. We can take a peek at that real fast here. So we'll keep our blue sine graph, and now what I'm going to do is the sine of x, and I'm going to add 2 to that. You notice that now the zeros are completely different. It is not crossing the x-axis at all, but the graph looks completely identical and has just shifted up 2 units. You can see the y-intercept here at 2 instead of at 0. If I switch this to be sine of x plus 3, now that's moving up to 3. If I subtract, that's going to move it down, so I could subtract 4, and now everything in my graph is shifted down 4 units from where we started. Same thing could happen for our cosine graph, so let's take a moment just to look at the cosine. I'm going to do the cosine of x here, remembering that the cosine starts at its maximum value of 1 and then moves its way down and back up again. If I do the cosine of x plus 2, here we go. The cosine of x, oops, I forgot my x in there. The cosine of x plus 2 is going to shift everything up 2 from where it was. If I have the cosine of x minus 3, now everything is going to be shifted down from where that was located. So same thing as our sine function, same period, same everything else, just shifting that up and down. All right, so that's our vertical shift, and the last part is the phase shift. Think about what happened in our functions back in chapter 1 when I moved something inside the parentheses. So for example, let's say that we had the graph of y equals x squared, and then we tried to compare what happened when we had x minus 3 squared. When that was changed inside the parentheses, we knew that that moved to the right 3 units. If I had y equals x plus 7 squared, now when it changed inside the parentheses, I know that that moves to the left 7 units. So the same thing's going to happen to us for our phase shift. A phase shift is essentially moving this left and right. So if I add pi over 2, that's going to move my function to the left pi over 2. If I add pi over 4, we're going to be going to the left pi over 4. And when I subtract, I'm going to be going to the right. So let's take a minute to just show you that on the graph. All right, so if I can get to the cosine function here, I'm going to do the cosine of x minus pi over 4 as my second graph here to show you. Notice that the cosine started at 1, so when x was 0, the y value was 1. And now look where the maximum is. This is the nice part about Desmos too, because you can just hover over it and it will show me nice and easily here that when the y value is 1, my x value is at pi over 4. So when we had the x minus pi over 4, that moved that value to the right pi over 4 units. If I switch this to be pi over 3, now you're going to see your maximum at pi over 3. Now it could be a radian value like that, pi over 3, but you might just end up with something like 2. Cosine of x minus 2. That means we're going to shift this graph to the right 2 units, and now you see your maximum happening at 2 instead. And then the only other thing that I want to bring to your attention is that I might have something that's 3x over 2. Well, now how does it move left and right if the coefficient is not a 1 anymore? Let's check out where that maximum is, 0.667. Hey, as a fraction, that's equal to 2/3. And so what's happening here, if we're going to figure out the maximum, is that we're looking for when is this cosine, when is the value inside going to be equal to 0? And so as I'm setting that up, I would be saying, well, 3x minus 2 is equal to 0. at an x value of 2/3 because you want the y value to be the same as it was when the x value here was 0. So we're making this inner degree part equal to 0 and finding out when that's going to happen. So 2/3 here. And so those are all of the things that we know about our trig function. So in summary, we have the amplitude is the absolute value of a. Your amplitude can never be negative because the negative in front just flips the direction that the graph is going, but it doesn't change the maximum or the minimum value. So it's always a positive value, absolute value of a. The period is not the b value exactly, but it's 2 pi divided by b. Again, if you were in degrees, you would instead say that that's 360 degrees divided by the b value. Now, when we're talking about these, by the way, when we're giving you this function, this is for the sine. This is also for the cosine. Okay, we're going to give you a couple changes for the tangent here in just a little bit. The phase shift, we just told you that basically what's in here, if we're plus c at the end, is going to actually go to the left. So that's why you get a negative there, to the left c units. And I also just show you an example where sometimes that b value isn't 1. And so we get the phase shift by doing negative c divided by b, just like you saw me come up with the 2/3 just before. So that's my phase shift. And then the vertical shift, one of the more straightforward parts. If I add d at the end, it's going to go up d units. If I subtract d, it's going to go down d units. Now this is all for the sine and the cosine. Let's say that we're talking about the tangent graph. In the tangent graph, remember that there is no amplitude. There is no amplitude ever, 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 no matter what number is there. So the a value, it doesn't matter what you have there. Let's say it was 3 times the tangent of 2x. There is still no amplitude. That 3 is going to stretch your graph, but there's no max and min. The phase shift, the vertical shift, those are going to be the same. But the other part that's going to change with your tangent is the period. Remember that the tangent of theta has a period of pi. And so if the period is pi, then to calculate the period, instead of 2 pi over b, it's going to be pi over b, or 180 divided by the b value. So just keep that in mind. Since the period is pi, that means when I'm doing the calculation of the period, it's pi over b, or 180 over b, instead of the 360.